I want you to take a look at problem number 1 and see if you can notice what's different about what you see there as opposed to what you've done already from chapter 5. Well, from chapter 5, hopefully you already recognize this, that we're missing an A and a B. Okay, so I do want to point out the difference here, and we're going to focus on this today. This is called which you should know this already, this is called a definite integral. Okay, so this is a definite integral, and a definite integral is a number. It's a real number. Okay, so we should know that already. It's a real number. Okay, a definite integral is, we talked about that, it's something physical. It would be the area between the curve and the x-axis, the net area. And so we get a real number. Nevertheless, the definite integral, we use the fundamental theorem of calculus, part 2, and we can find an antiderivative of lowercase f and evaluate that. So we already know how to do all that. Okay. Now, what you see here is we see that we don't have limits of integration here. We're missing these limits of integration here, and that's not a mistake. What we call this is I guess I can put a box around this. This is called an indefinite. Okay, indefinite integral, and that's exactly what it is. An indefinite integral, as opposed to a definite integral, is an integral that we don't know a number. It's actually a function. Okay, and an indefinite integral, actually, it's a family of family of functions, of which we can find an infinite number of antiderivatives to this. So let's take a look and see how we do this. In fact, we're going to use this space over here to the right. We're not even going to do that problem right now. We know that if f of x is equal to, let's say, 2x, we know that lowercase f of x has an antiderivative, and one antiderivative, which we already know, is x squared. Y equals x squared, or capital F of x equals x squared. However, keeping in mind that f prime of x, then, which is equal to lowercase f of x, would be 2x. Okay, well, that's all fine, but what happens if we just add a constant? Capital F of x is equal to x squared plus 1. Well, guess what? F prime of x is still equal to 2x, and so what we see here is that lowercase f of x has not just one antiderivative, but it has another antiderivative, and you can just keep changing the constant that you add to the x squared, and as long as you add only a constant, then the derivative of capital F of x would always equal 2x. Okay, so we call the family of functions x squared plus c the family of antiderivatives of the function f lowercase f of x equals 2x. So we would say f of x equals x squared plus c would be the family of antiderivatives. Okay. Well, how do we apply that to our indefinite integrals? Well, when we have an indefinite integral, that would be synonymous with saying an antiderivative. Find the antiderivative of this function here, x squared minus or plus 4x minus 1. So we're going to do problem number 1 now, and we would say that the integral of x squared plus 4x minus 1, and we could call this the antiderivative of x squared plus 4x minus 1, would equal x cubed over 3, because we know that we just have to use the power rule in reverse for antiderivatives, meaning that we add 1 to the exponent and then we divide by that number, plus 4x squared over 2 minus 1x to the 1 over 1, but then we have a plus c. So we just found the antiderivative, or the form of the antiderivative for the function x squared plus 4x minus 1. So that's the answer. That's all I really need you to be able to do. Actually, it's part 1 of what I need you to be able to do before you come into class tomorrow, is just add a c to the to the antiderivative that you were finding using chapter 5. So just add a c because it's a constant, because these antiderivatives all differ by only a constant, because when we do take the derivative of the antiderivative we get the integrand, and when we take the derivative of that constant we just get 0. So that's why that constant is there, because it illustrates that all of the antiderivatives differ by just that constant. So see if you can do number 3 on your own. Find the antiderivative of 2x dx. That's your job right now. Pause the video. And we would just say 2x to the 1 plus 1 is 2, but we have to divide by the 2. And then we add the c. Don't forget the c. And then we can cancel the 2's, and we just get x squared plus c, and that's it. That's the answer. Okay. Well, nothing fancy so far. We could do a million examples like that, where all you have to do, remember, is if you're evaluating an indefinite integral, then you just add the c, and you don't have any. You don't have to evaluate any antiderivative at an upper limit of integration or a lower limit of integration. But one thing I did want to point out is you might be thinking to yourself, well, why are we just talking about c's now and we didn't talk about c's before? Like, let's take this same example. Okay, let's use a different color. Let's say we want to integrate from 0 to 2 of that same function that we just found the antiderivative for, 2x dx. Okay, well, let's say we use that c. Let's say we put the c in there. Okay, we'd get, not at 2, but we'd get x squared plus c, and then we'd evaluate that from 0 to 2. Okay, well, if we evaluate that from 0 to 2, we would get 2 squared plus c. Now that c would just be some constant. It would be a number that's fixed, okay? Minus 0 squared plus c. And so we would get, noticing that the c's are going to cancel out, c minus c. Let me do this first instead of just doing that without showing the work. We'd get 4 plus c, and then we'd get minus 0 minus c, and we would just get 4. So in other words, the reason why we haven't talked about that constant yet is because the constant would just cancel itself out when we evaluate the definite integral, because that's exactly what we did. This is a definite integral. Okay, and if we had just chosen the simplest antiderivative of x squared without adding a constant, and the constant otherwise would be 0, or I guess we could say we're adding a constant and that constant would be 0. But anyway, the simplest antiderivative would be x squared, and if we just use x squared, we would get 2 squared minus 0 squared, and we'd get 4 anyway. So the definite integral's value is for whether we add a constant to the antiderivative or not. So to summarize what I just said, using a lot of words, we didn't introduce the c before because we had no need for it. Now we have a need for it. In fact, we're going to be solving, so to transition over to example number 4, you see here, we're going to be solving what we call differential equations, and we're going to talk more about that all that terminology as far as differential equations, the solutions and slope fields and things like that. But I really just want you to be comfortable with, number 1, the notion of when we see an antiderivative, in other words, an indefinite integral. So I want you to be able to add the c to the antiderivative, okay, getting a family of antiderivatives. And then this next part of the problem is, if we want to solve for that c, what we really need is we need an initial condition, and I do want you to make note of that. This is what we call an initial condition, and here's what I'm going to do. I'm going to erase some of this stuff, okay, and so we can focus on the task at hand. And the task at hand, hopefully you've taken good notes. If you didn't write that stuff down, you should rewind the video and write that stuff down. So I want to have a clean slate here. In fact, I want to cover up all this stuff. I I guess before I cover this up, I wanted to point out here that just what you remember to be true, in which when we talked about our capital F of x in Chapter 5, we knew that we referenced that being the antiderivative of lowercase f. And anyway, when you go to the right, you're taking a derivative. You keep going to the right, you keep taking derivatives. When you go back to the left, you're finding antiderivatives. It's the same case if we start with a y and we move to the right. We get dy dx. We move to the right again. We get the way we notate that second derivative using this notation of dy dx is the d. It looks like a d squared y with a dx squared, but it's really, this is the second derivative here and this third derivative over here. Okay, and the same thing when we have motion problems in which we have position, velocity, and acceleration. As we move to the right, we take a successive derivative, and as we move back to the left, we're finding antiderivatives. And so this is all related to the stuff you've done from Chapter 3 on. And notice here that in problem number 4, we have a dy dx is equal to 2x. So in other words, we have the derivative of a function equals 2x. Okay, well fine. Let's cover this stuff up here so we can have lots of room. We have an initial condition, and that's what I had said before. I want you to write that down. Initial condition. Now, if we're told basically where one value of the function is at a certain time or at a certain moment, then we can use that information as to help us figure out an exact value for the function. Okay, because if you think about it, well, I won't go too far into it. Let's just do a couple problems and then we'll talk more about it in class. For dy dx equaling 2x, we know that y, we just showed that y is equal to x squared plus c. Okay, because y being the antiderivative of dy dx, we showed that the family of functions, family of antiderivatives, was x squared plus c. But again, we're told that y of 1, in other words, when x is 1, y is 5. Okay, so we're just going to replace y with 5 and x with 1, and we can find the exact value for c, given that if we just subtract 1 from both sides, we get that c is equal to 4. And so therefore, we know that y, the specific solution, this is the general solution here, general solution to the differential equation. Again, we'll get more into the terminology when we get to class. But the general solution has basically just x squared, the antiderivative, plus some constant. But the specific solution would be y equals x squared plus 4. And that is the solution to the differential equation. This is the solution. Solving, yeah. Solution to the differential equation. I'm gonna abbreviate that as DE. So the solution to the differential equation, and more specifically, it's a solution to the. Oops, my bad. So just like what I was saying, this particular solution here is the solution to the differential equation, the general solution, and then we have the solution to the initial value problem, the specific solution to the initial value problem. So that's what this is. It's an initial value problem because we're given an initial condition to the differential equation, and there's lots of terminology here that it'll become second nature to you, but it is important that you focus on that and try to understand the big picture, because that's the hardest thing about learning this new material, is that we've got all this different terminology. So I'm going to do another video for you guys to practice a couple problems, and then we'll go from there. So again, though, the two things I want you to be able to do is to find an indefinite integral, evaluate a indefinite integral, and also to solve an initial value problem. So those are the two goals before you come into class tomorrow.